Yeah. And now I think alphabetically, Harshal, could you introduce yourself? It will be great.
Hello everybody, this is Harshal Shah from Los Angeles. I'm working with Artisan.com and I'm a Java developer come software architect.
All right. Thank you, Harshal. Huda, could you unmute? Is it possible for you to unmute and introduce yourself? Vikas, could you mute yourself?
Hello.
Yeah. Yeah,
Hello. Hi,
Vikas.
this is Vikas.
Okay.
Uh, Hello, Vikas. Actually, I am working as a Java developer in Infosys from last
Okay.
2-3 years.
Okay. Okay. Thank you. Thank you, Vikas Mishra.
Hello, are
And
you able to hear me?
yes, yes, I'm able to hear you. Everybody is able to clearly hear you. All right. Thank you, Vikas, for the introduction. All right. So, Huda, is it possible for you to introduce yourself once, or should I move to the next person? All right. So you'll have to unmute yourself and then you introduce and then mute. Yeah. Uh, did you introduce Huda? Could you unmute yourself and then introduce? Yeah, I still not able to hear. Yeah. Me too. I'm not able to hear you, Huda. So just unmute yourself and then I think some hardware problem. So I'm moving on in case, yeah. So Malvika and Amar, could you introduce yourself? I am unmuting you. Okay.
Hi, this is Malvika.
Hi, this is Omar.
We are both software engineers living in San Diego right now.
Okay, okay, okay. Great. Great to know you, Malvika. Where are you located?
Seattle.
Okay. Great, great. All right. So, Minu, could you unmute yourself? It's okay. Yeah. And
Yeah, hi everybody. I'm Meenu Chatut. I'm working in Sintel as a Java developer and I'm located in Phoenix.
great, great. We have a wonderful set of people. Nalini, could you introduce yourself?
Yeah, hi, I'm Nalini. I stay in Dubai and I'm from market research background.
Okay, okay, great, great. And Nitika?
Hello everyone, my name is Nitika Sharma and I'm working in India but as a associate software programmer and I'm from Ghana.
Great, great. And Pop, could you introduce yourself?
Hello everyone, this is Pop. I am studying as a database specialist now.
Okay,
Thank you.
great. Nice to know you, Pop. So, Sanjay, could you introduce yourself?
Hi, this is Sanjay Sarma. I'm in Arlington, Virginia, in the Washington, D.C. area. Most recently, I was working at Deloitte in their healthcare innovation practice, and I'm looking for the next opportunity in the big data healthcare space. I am not a developer by trade, so this should be interesting.
Okay, yeah, awesome. Yeah, great, great. So Shweta, could you introduce yourself?
Yeah, sure, Sandeep. Sandeep, I'm working as a in American Express through Centel. I'm working in Java development and open source area. Uh,
Mm-hmm.
that's it. Yeah, and
Okay.
I'm located in Phoenix.
Oh, great. Oh, great. Yeah, Sayed. Great.
Hi, everyone. I'm Ali, and DC, I'm working as a principal engineer with MDocs.
Great.
Can
Great.
you hear me?
Yeah, you could hear you. Yeah. Thank you, Sayed. Tarak, could you introduce yourself? Vikas Goyal, not Mishra. Yeah. We can only hear some typing and cracking sounds, actually. I can't hear anything. So Vikas, I could not hear anything from you. We hear the cracking sounds.
Hello,
Yeah.
hello.
Yeah.
I'm Huda. I'm a teaching assistant at King Abdulaziz University in Computer Science College.
Okay. Okay. Great.
And
Great.
I have a master's degree, and I'm a student, master student. And my thesis is on big data and mining on big data.
Excellent. So you are from which location?
You are Saudi Arabia, Jeddah.
Great.
Yeah.
So yeah. Did
Thank you.
Yeah, thank you. So did we miss anybody? I hear some other sounds. So yeah, Vivek, could you introduce yourself?
Hello.
Yes, we can hear you.
Yeah. Okay. Sandeep. Hi, Sandeep. Hi, everyone. I am Vivek, and I am attending this class from Noida,
Great.
and I work for Sienna. Sienna is a telecom company. You might be aware of that. Sienna is in Gurgaon, so I work for Sienna. Before this, I have worked with HCL Technologies in Noida and RBS Royal Bank of Scotland that was in Gurgaon.
Great.
So I
Yeah.
have a total Java development experience of around 9 years.
Mm-hmm.
It has been mostly into core Java based applications having heavy use of concurrency and all that.
Okay.
But I have no idea about big data before this class, so I'm looking forward to it.
Great. You're going to have a good time, I assure you. So yeah,
Yeah.
you can mute yourself. Yeah. Then uh, all right. So yeah. So I think we have covered everybody for the introduction. So is there anybody who hasn't given the introduction of themselves today? All right. So these are the best 12 minutes we have spent, and oh, okay. How much time? All right. So yeah. So how big a break do you want, Huda? Just 5 minutes. So is everybody okay? Because other people also have told me similar thing that instead of having a big 10 minutes break, if we have 5 minutes break at 1 hour, it will be better. Does it make sense? All right. So we'll try to have the break at at one hour instead of having 1.5 hour long break. All right. All right. So in case I forget to take a break, somebody please remind me. Great, Tarak. So, okay. Okay. Is my voice breaking to somebody else other than Vivek? If it is so, then I'll switch my net connection quickly. All right. All right. Great. Great. So we have, so I think Tarak is the only one who hasn't given his introduction. So do you want to give introduction, Tarak? So please unmute yourself and then give your introduction, then mute.
Hello everyone.
Yeah, Tarak.
Hello.
We can hear you, Tarak.
Hi everyone. I am Bharat from Bangalore. I'm working uh, Tech Mahindra as a testing engineer.
Okay.
I think that.
All right. All right. So we are muting you back. Okay. All right. Thank you, Tarak. Thank you. Although we were not able to hear you clearly. So Tarak is from testing background and from Bangalore. All right. All right. Yeah. Great. Great. So we have wonderful set of people in the session now, 18 people, and all of them are from different countries and from very different backgrounds. So keep your questions coming. I'm sure. I'm sure your question, other people might also be having same questions. Okay. Great. Great. So before we start, we will. Do you want a little bit of a recap of what we discussed yesterday? All right. So let me just go over to the previous sessions one. So yesterday, the most concrete part which we discussed was the HDFS one. We talked about in general what is big data about, and in conclusion, if I have to summarize my whole presentation of yesterday, first half of presentation, the idea was that, oh, sorry, I'm extremely sorry. Now you can see the screen. All right, thank you. So if I have to summarize everything quickly from yesterday, so first is big data is about distributed architecture. So when we have humongous data, single computer cannot solve. Therefore, we need distributed architecture. And when you reach to distributed architecture level, then you start calling your data as big data. Right. So that was first part. Next was that Next was, if I have to summarize further, the other important part with respect to big data is more data is better than better logic. If you have an algorithm which computes the average value of a movie rating, no matter what kind of algorithm it is, if you have more number of data, the data rules over the algorithm. If you have to come, either you are very clever, you're trying to gather insights from very small data, or you have a very dumb algorithm which does insights over a humongous data. So this algorithm which just computing a basic average, median, or something of that sort over big data any day will win over a clever algorithm. And the reason is that the law of large number says that if you have bigger data, the the insights will be far more useful and it will be far more better and averaged out. Okay, so that's all about the big data, and on the same basis we have various kinds of interesting problems to solve on top of big data, because data speaks better than the logic. All right. And therefore it's important to know about big data. So Hadoop is all about distributed computing that handles humongous data. All the components which are part of Hadoop are all about distributing computing. Okay, so we'll talk about that. So before that, we talked about the most important component of Hadoop ecosystem, that was the file system. So file system, in a very simple words, is made up of admin node, single admin node, and multiple data nodes. This admin node keeps track of where is the data, while data nodes keep the actual data. And each file is broken down each file is broken down something called blocks, and these blocks are by default in today's time 128 MB. Earlier they used to be 64 MB. And so a big file is broken down into 128 MB blocks, and each block is copied onto multiple machines. Okay, each block is copied onto multiple machines. That is called a replication factor. The value of replication factor is 3, which means each file, if you are pushing onto your HDFS, is going to take 3 times the actual storage. Okay, because the file is actually having the 3 copies over your network. All right, now in this, why do we have replication factor of 3? So that in case one machine goes down, all the blocks that are lost because of this machine going down, those blocks are copied from the existing blocks. So every block that gets lost must be having a copy somewhere in the network in case the replication factor is greater than 1. In case you have set replication factor as 1 of a file and the block is lost, then that file cannot be recovered. It'll give an error saying cannot recover the file. Yeah. So Vikas's question is good. Why not 64 MB? Why not 256 MB? Why is it 128 MB? The simple answer is it's mostly arbitrary. The fact that some of the installation is still have 64 MB and most of the other installation have 128 MB, it's mostly arbitrary. Okay, the way it is, it's mostly empirical. It's mostly empirical. Okay, replication factor is can be set by the client. So yeah, okay, let me repeat this again. So the replication factor, first is the block size. First question was the block size. Block size is 64 MB. Earlier it used to be 64 MB, now it has become 128 MB. The simple rule was your block size should be smaller than the smallest disk that was possible at any point of time. So b- so in case you have 1 GB block size, then there might be 1 GB disk in the network which you want to still utilize. Therefore, you cannot really have a 1 GB block size. Therefore, it is kept in such a way that block can fit on almost every storage device connected to HDFS. Alright? So it should not be too big. If you have too big, then it cannot fit and the movement will be too much of a problem. If it is too small, then gathering the data over the network will take too much of time. Okay, so empirically it has been decided to go ahead with 128 MB. Empirically means based on certain statistics. Okay, now Harshal's question is what happens in case error occurs. So it will roll back the whole process. Yes, it will. I'll give you an example. So let's okay, let's go back here. So a user comes in, the user has come in to write the files, okay? And when the user tries to write a file into HDFS, first of all, it goes to the name node and creates an entry that, hey, this is the file we want to create. Now, name node tells the client back that go to these data nodes and please store your blocks. Okay. First block goes to data node 1, second goes here, third goes there, and so on. Now, as soon as the client finishes the work, it goes back to the name node saying, I'm done. In case client faces an error here and is unable to store the data for some reason, it either informs name node or it gets killed in between. In either of the cases, name node will delete the entry which was created. This dirty write, the uncommitted write will never be reflected. Okay, does that answer your question, Harshal? All right. Now let me answer. So the next question is, replication factor is set by client or its default. So by default, the replication factor is 3. I'll show you that how to add a file onto HDFS. And by default, the replication factor is going to be 3. All right. In case, in case you want to change a replication factor, you can change the replication factor at later point of time also. Later point of time, you realize that your file is very important and you want a replication factor of 5, so you can set the replication factor, as well as you can reduce the replication factor later point of time. Similarly, while adding a file, you can specify that I want to add this file, but my replication factor has to be this much. All right. So that was an Nitika's question. Yeah, by default, it is always 3. All right. And also you can set it to be something else from the admin panel. You can specify on HDFS saying keep my default replication factor as 15 or 4 or 6. Whatever you want, you can do that also. So every file you add by default will have, if you have set the default replication factor as 4, so all the files you add to HDFS, they will have replication factor of 4. All right. So it's fairly flexible. Good. All right. Let me answer some more questions. Yeah. So again, Nitika's further follow-up question is why 3, why not 4, why not 2? Okay. So let's try to think in this way. So why not 2 first of all? That is probably the most common answer all of us have, that we generally keep a backup of 2. Why not 2? Okay. Now, there's an important insight you have to look here. So let's say you have this network, data node 1, data node 2, data node 3. All right. And the moment one node goes down, it's not only uh, one file which is getting lost. It is all the blocks that are getting lost. Okay. So in case one in case two nodes go down suddenly, your you will suffer humongous loss in case your replication factor is set to 2. All right. So in case your replication factor is set to 2, you will suffer humongous loss. Why? Because if you have 1,000 files and one block from all these 1,000 files is how much? 128 into 1,000, right? Which is 128 GB. which is fair enough to assume that one data node might contain thousand blocks from different files, thousand files block, right? This is fair enough to assume, right? Because what disk can be 128 GB. Now, the moment one data node goes down, all these thousand files will go useless in case there is no replication. Similarly, in case two data node goes down and you have a replication factor of 2, then you will suffer a humongous loss. Now, two machines or two disks going down is a fairly common thing as compared to three machines going down at a certain point of time. Okay, so as compared to three machines suddenly going down, the probability of two going down is much more higher. That is why, and you basically do a risk analysis. Say, in case my two machine go down, we will actually lose 2000 files, right? All those files which are having blocks here. So therefore, a little better than our normal backup. In our normal backup, we generally store whole files, and therefore, in case one machine goes down, whole file is available. This one is little more risky because we have blocks, and in case all the blocks go down suddenly, will suffer a humongous loss. Therefore, this backup has to be little better than our usual one, and having three machines fail in a duration of say 5 minutes is a very low chance. All right, did it make sense to you? Because I'm saying 5 minutes because within 5 minutes of time, HDFS will recover from the loss by replicating and bringing the replication factor up to 3. So that is why it has been decided to take replication factor as 3. Also, in case you are using solid state drives, just like the way we are using, you can have a replication factor of 2. Reason being, the chances of failure of a SSD, solid state drive, is lower than your usual hard drive. Make sense to you? Herschel's question is, when does replication happens? So the moment a data node goes down, when the data node goes down, name node will not receive ping from the data node. So all of these machines keep on pinging each other, telling about their presence. Specifically, all data node keep on informing name node about their presence. And in case one data node has not informed name node about its presence for some time, name node assumes that particular data node has gone down. So all the blocks that were located on data node has been lost. Therefore, name node informs other data nodes to start replicating because one data node has gone down. Okay, so this replication keeps on happening all the time. The moment data node goes down, replication happens, and I mean regeneration of the replication happens. And in case you are adding a file, then also replication is happening, and the replication happens between the data node. Name node does not read the data and write back to some other data node. Name node just informs one data node to start copying data from another data node, and so on. Make sense to all of you? All right. If some node goes down, then how that data node will replicate the other? If some, yeah. So let's say, I think I would make a diagram. How can I better explain? Right. So I say so sketch. So in the beginning, let's say that we have 4 nodes. Okay, we have maybe 4 nodes, right? All of them are having block 1, okay, block 1. All these three are having block 1. Make sense to you? So in the beginning, these are 4 data nodes. This is my one data node 1. This is my data node 2. So when I say data node, it's generally a separate machine, but you can think of it as a process. Process as in process listening to a particular port. Okay, it's a network daemon. Just like your mail server keeps running on one machine, similarly data node can also run on one machine on a particular port. All right. Now there is a file whose first block is located on data node 1, 4, 5, not on the 6. Okay. Now suddenly what happens is this block goes down. Okay. This block goes down, as in this data node is dead. Okay. So data node 4 is informed, data node 6 is informed to get the copy from data node 4. Okay. So now after some time the block 1 will be available here. So again, now block 1 is available at 3 machines. So Vikash, does it make sense to you, Vikash Mishra? All right. So the replication happens to another node that is empty. Yep, that is how it is. Because it does not make any sense to copy 2 blocks on the same machine. Why? Because on the other node, yes. Why? Because these are copies of the same data, and the only reason we are copying the data to another machine so that we have a backup. In case there is no machine available, now after some time, let's say it goes down here. Data node 4 goes down. Now we are left with only 2 nodes. Then it will give an error. It will throw an error to you saying we don't have enough data nodes to promise a replication factor of 3. And this file becomes unavailable, and the administrator is immediately informed that this particular file has gone below the replication level. So again, this replication happens, the actual data transfer happens between the nodes, between the data nodes, but name node is the one who takes care of this accounting. There is this name node standing here, which is listening to the pings from all these nodes. Okay, this is our name node. It keeps on figuring out which one has gone down and which one is up, and it informs these data nodes to start copying amongst themselves. Make sense to you, Malvika? So it's both name node as well as data node. Name node informs the data nodes to get the copy, while actual data is copied between the data nodes. No, there is no replication factor for name node. The only thing we have is something called secondary name node. Okay, we have something called a secondary name node. All right, which is basically a copy of whatever is the name node. It's exactly the ditto copy of the same. Okay, so let me just copy this, so you can think of this with a different color. All right, so Name node is the one, while secondary name node keeps a copy of it in the background. Okay, it keeps on uh, taking the data back and forth. Okay, and everybody, even data node, keeps on talking to this as well as this block, this as well as this. All of these are talking. So all of the data nodes inform to secondary name node as well as name node, while name node keeps a copy of the data on secondary name node. So secondary name node is always up to date with respect to all the metadata, just that it's sitting silently and doing nothing. The moment name node goes down in a high availability setup, secondary name node takes immediately the place of the name node, and the whole process keeps working. So we don't have 3 copies of the name node, we just have 2 copies of the name node. Make sense to you? All right. So name node needs to be very secured in the whole system. Yes, name node has to be really, really fast, and name node has to work really, really uh, in a stable manner. Also, please note that name node keeps all the metadata in the memory, while the actual data is also kept on the disk. Most of the metadata, almost all the metadata is available in the memory. Therefore, if there are too many blocks, if there are too many blocks and too many small files, they will quickly fill up the name node. The name node's memory will be quickly filled up if there are too many files. At that point of time, what name node will start doing is it will start creating the blocks of bigger sizes. Okay, name node will start creating the blocks of bigger sizes to reduce the metadata. All right, so now you can see that if your files are too many, then they are going to hit name node very badly, and hence you would require huge RAM in the name node. While building your cluster, you have to make sure that name node has bigger RAM as compared to the data node. So name node generally starts, although you can have as big as 64 MB RAM in name node, there is no lower limit actually. But generally, to run a proper Java program, because all of these are Java program and Java virtual machine has to be run for all of them, you generally keep at least a 4 GB of RAM in name node. If you are planning for a petabyte of cluster, then you will have to have something like 8 GB or 16 GB RAM. Okay, but it's more of a function of the number of files you're storing in the cluster. Okay, so yeah, Sanjay is saying, why do the nodes keep communicating with secondary name node? Can't it get everything from name node? Very good question, Sanjay. Now let me explain this. So the overall objective here is reduce the load on name node, right? And but we cannot compromise on the consistency of the data. Therefore, we have to have a singular name node. We cannot have two name nodes running in the network, both of them creating files simultaneously or modifying simultaneously. Therefore, name node has to be singular. Also, we cannot serve read requests from the secondary name node. Why? Because if you start serving read request, say you are just reading the file, you are not writing the file, you want metadata from the system, and if a secondary name node starts serving it, then you might be getting the metadata for a little older system, because it takes time for data to go from name node to secondary name node. So secondary name node will have a little older data. Therefore, In favor of a very strong consistency, HDFS does this trade-off that let's run only a single name node. Now, having a single node, a single point of failure, or single machine which handles all the load is too much for a single. I mean, it restricts you. That is why in whole of the design, everything has been delegated to each individual data node. We try as much as we can, we try to offload the work from name node to somebody else. And that is why instead of the information going from data node to name node and name node replicating the same thing onto secondary name node, each data node keeps updating name node as well as secondary name node. Okay, somehow this somehow the secondary name node, uh, I mean, this basically would reduce the load on the name node a little bit more. Make sense? So imagine this. For everything that goes wrong with data node, if it informs only the name node and then name node informs secondary name node, so name node is being overloaded. Okay. Instead, data node informs name node as well as secondary name node. This way, both of them are equally updated at the same time without without one more hop of the information from name node to secondary name node. Make sense to everybody? Replica is always not really the way replicas. Nitika's question is good. So the question, let me rephrase her question. Her question basically, can be rephrased like this: if you have a file and you have 10,000 nodes in the cluster, or let's say you have just one block which is 120 MB file, which all node will contain the three replicas of it. Okay, that's a ever going challenge with Hadoop. Okay, question is that we have 1,000 nodes available in the network. Where should I store the replicas of this file which has just come in? Okay, the general thumb rule is first copy goes immediately to the closest one. We will talk about it in more detail, where how does Hadoop decides which one is closest, but for time being, let's assume that Hadoop has been configured to know the distances between the nodes. Okay, and Hadoop has been told that these nodes belong to the same rack, these nodes belong to another rack, and so on. So first copy of the data, first copy of the block goes to the very closest node, and other remaining two copies of the block go to another rack. Another rack as in each rack contains multiple computers. Each rack is a subnet in itself. And so first copy goes to the same node, the closest node to the writer of the data, and other two copies go to off the rack. Off the rack can be another data center or could be another just in the same data center another machine. So that is something they try to do it. Okay, so the idea is if your data is located very close by, if both the replicas of the block are located very nearby on your rack, in case there is a fire, all the replicas will get lost. Therefore, you try to spread out the data. But in case your replicas are really, really far away from each other, so when the reader comes in and the node containing the first copy of the data is not available, then the next replica will be far, far, far away for the user, and therefore reading will take time. That's why the the challenge is to keep the replicas of a block well spread out in the network. Okay, and there are multiple algorithms. The whole algorithm has gone a change at least 4 or 5 times, and it's ever changing. All right, makes sense to all of you? Now I think I have missed few questions, so if you can just copy paste your question, it will be difficult for me to go through. Are the data node intelligent? Do they keep track of what has been copied to name node, primary and secondary? How it happens in case of name node goes down and comes up later? Yeah. So okay. So these are the two questions. So let me repeat Vivek's question. Now, Vivek's question is, are data nodes intelligent? Of course, they are intelligent. They are the programs. Each data node is basically a process, just like your mail service or any other service which you run on a computer in the background. Similarly, data nodes are nothing but a service. All right. So on one machine, you can run a data node service, you can run other things, and so on. Perfect. Now, these data node processes are smart enough. You put a logic in that, and they keep track of what they have written to name node. Okay, what is it that they have informed to name node? That is their duty, and they fulfill that properly. Okay, and data nodes have this algorithm in place that they have to write to name node and secondary name node if secondary name node is configured. If secondary name node is up, only then data node write to the secondary name node. Okay, but data node do not impose this restriction. Data node does not impose this restriction of mandatorily having a secondary name node. All right, last time when we show you I showed you our cluster, our secondary name node was down, and it's still down. We have not put it up. All right, now question is how it happens in case name node goes down and comes up later. So the way it happens, when the name node goes down, suddenly the focus shifts from name node to secondary name node. In case there was some change which happened on name node and did not shift to the secondary name node, then that change is lost. That's a little bit of a loss you have to suffer through. Next is, now our secondary name node is the current name node. In a high availability setting, what happens is, if the this older name node, so it went down, and after some time this went down, and let me just mark it. This went down, and after some time it came up. So what will happen is, when it comes up, it will remain as secondary, and it will keep on synchronizing the data from the current name node. All right, and it, it will wait in case the secondary name node is going down. In case secondary name node is going down, then that name node again becomes the primary. Hope you got my point, Vivek. Now, all right, yeah. So now let me explain again. So what happens is, this one, I will actually make a little bit of annotation. I'll make a crown somewhere. Do you see a crown? Yeah. So yeah. So here, this one went down, this one went down, and so now this one is up. Okay. So this one will become your primary now. This is your primary. After some time, this one comes up. And there is no, at this stage, there is no primary right now. Okay. Now after some time, this one comes up. So this one is up now. So this one will stay as secondary. This one will stay as secondary and will synchronize its data from current primary. Okay. This will synchronize its data from current primary name node and keep on synchronizing it till the point they reach to the same level. And once that is done, and in case in future if this name node goes down, this current secondary will become primary, and this will keep on going on. Make sense to you now? So sync is between both. Sync is between name node. That is why I have drawn this diagram. Sync is between both name node and secondary name node, as well as data node inform to both secondary as well as the name node, primary name node. Okay. Perfect. So I'm hoping everybody is on the same page. Now let me answer Harsal's question. How much memory is required for name node? Okay. So name node by default can even run in 1 gigabyte kind of memory or 512 MB kind of memory, because what is a name node? Name node is again just another process. And what is a process? Process is a Java program which has been programmed to keep on running continuously, reading data from a particular port or a socket, listening to a socket, and waiting for somebody to uh, put data into the socket, and it keeps on reading that and keeps on waiting for the socket. All right, that's something called a process, a service which is running in the background. Now this since this is a JVM, so JVM by default at least requires something like 128 MB of memory to run function it properly. So that's a minimum amount of memory. Now, how do you compute? You generally compute based on how much data are you going to store into your cluster. Say you have decided that there is a petabyte cluster you are going to build. Okay. And you generally have this thumb rule of saying that for each gigabyte of data, you are consuming you're consuming something like 100 bytes of memory at name node. Okay, so 100 bytes of memory go for each gigabyte of data, and therefore, so if you have 1000 gigabyte, which is 1 terabyte, so 1 MB will go for uh, so 100 bytes into something like 100 bytes into 1000, so 100 MB memory will go in case you have 1 terabyte of data. uh, 100 MB is 100 KB will go, sorry, 100 KB will go for 1 terabyte of data. And same way you can do the computation. So for petabyte you will reach to a few gigabytes of RAM, which has to be capped for kept reserved for the metadata. Okay, so that's how you generally come. Okay, so yeah, thank you, Tarak. That is a better way. Yeah. So yeah. So so since name node is going to store metadata, what is a metadata? Name of the file, name of the files, and for each file, for each file, what is the okay? So we can say list of these things called file, and for each file we have name, how many blocks does it have, and for each block how many replications, and where are replications located, which data nodes are replications located, right? And so on. Okay. So and for each file, the size of the file and permissions, etc. Okay. So this is the name node metadata. So you can assume that for each 1 gigabyte, you will consume around 100 bytes of information. Okay. Bytes of memory, 100 bytes of memory or metadata. Okay. So for when you store 1 gigabyte of data, I'm assuming that it's a single file. Yeah. Replication factor, and for each file we have replica factor, right? Replication factor, that is correct. Thank you. All right. Now, so you can assume, all right. So do you want to take a break quickly for 5 minutes? All right, let's take a break. We'll be sharp 9:35 back. All right. Okay. All right, so I'm back. Let's start. So I was telling you that 1 GB of data might take 100 bytes of memory of metadata. Okay, so is everybody with me? Great. All right, so yeah, 1 GB of memory might take around 100 bytes of memory there. And so you can assume that 1 petabyte, which is 1 gigabyte, will take around 100 gigabyte of RAM. Okay. So now you can see that beyond 1 petabyte data, HDFS will have a really tough time. Now, what will HDFS do in case the RAM starts becoming inefficient? Okay, if the RAM is not sufficient, so it will start it will by default it will start increasing the block size, and that will reduce the total metadata, and thus increasing the amount of memory that can be stored, amount of data that could be stored on your cluster. Okay, or you can again, if your data is growing bigger and you have only 100 GB RAM, what you do is you basically increase you basically increase the size of the block such that instead of taking 100 byte of the data, it will start taking 10 bytes of the memory for each GB. Okay, if you increase your block size to 1 GB instead of 128 MB, then it will start taking 10 bytes of memory, and therefore then you can handle up to 10 petabyte of data. Make sense? So lot of this magic HDFS does for us, and some of it you can also instruct it to do. All right. So what was the other question? So I got a question from Vikas. His question was related to Mahout, which is basically a library of algorithm. So in case you are aspiring to be a data scientist, I would strongly recommend to go for Mahout's online documentation about various algorithms available. Okay, have a look at it. Okay, so that was answer to Vikas's question regarding the documentation. Now, but the block size depends upon the average size of files. And that is Vivek's question. The block size by default is hard as in 128 MB. Okay, but it changes, or you can change it when the data grows bigger and your RAM is becoming inefficient. Okay, it does not depend on average size of file. It is just that, Vivek, it is just that the default size of 128 MB has been computed based on certain empirical or average value of various files. Okay, so it is actually up to you absolutely how big your block has to be. Okay. Also, please note that in case your files are very smaller, 1 KB will take the similar amount of metadata as 100 MB will take. Okay. Yeah, RAM of the name node. That is correct, Sweta. So in case you have very humongous number of small files, say 1 KB each, so each 1 KB file will take the whole block. A whole block as in it will take the metadata equivalent to the one full block, right? So whether a file is small or big, it generally takes similar amount of memory at the name node level. Therefore, we always say that HDFS is not really great when it comes to handling very small files. Okay. So what we do in such case when you have say a million, 1 million 10 KB files. So the general strategy is to zip them with a compression called LGO, LZO, okay, and that way the so the LZO has this property that even if the files are sliced, still the data can be decompressed. All right, so that is how. So what you do is if you have a million of 10 KB files, you basically combine them together and make it say 10 GB file, single 10 GB file, and and then you push it to HDFS. Okay, and then you can operate upon the individual section. This is called either RCA file, or there is another named. We will talk about that in future. Okay, it's a binary file. We'll talk about in future. All right, so we talked about multiple things. We talked about the memory of the name node. We talked about how is the block size decided. Yeah. Now, so yeah, good question, Sayed. So the way this compression has been designed bottom up, that that basically it will not take too much of time. This compression is fairly efficient when you have to access files. Okay. The header of this zip compression will contain the information about which all files are there, and then it should not be much of a problem to retrieve such a file. Okay, so HDFS has been tuned for this algorithm. The LZO algorithm works pretty well with respect to the HDFS. All right. So after Vivek, there was the question: what is the ratio of memory of name node versus memory of data node versus metadata? What I did not get. Tara, could you repeat this question? This seems to be very important. What is the ratio of memory of nodes? So which one are we talking? So yeah, ratio of memory of the file. Yeah, that's what I was saying. So generally, even if the file is smaller, whether it's small or big, they are going to take equal amount of memory metadata. Say one file is 1 KB, another file is 100 MB. They are going to have a single block, right? And therefore they are going to have equal amount of memory in of metadata, equal amount of memory, or we can say the metadata, because metadata is stored in the memory, and this 100 KB generally for each file around 100 bytes of memory is consumed. Okay. So that's a general thumb rule. I need to see what's the current status. Okay. As and when SDFS keeps improving, they keeps on changing this number. All right. Does name node throw error when write contention is very high? What happens at that time? Okay. So come again. I need to understand what exactly do you mean by write contention being high? You mean to say when we are trying to write too much of data, does name node throw error? Is that your question, Harsha? Or in do you mean to say that our intention when we want to write? Okay, so yeah. So it doesn't, a name node doesn't throw an error. Name node, all right. So yeah, name node does not throw an error when the when say we are writing data at a very high speed, and name node would not throw an error. So okay, let me understand the question. His question is, what happens if we are trying to write at a very fast pace and name node throws error? In case in those cases, your API, whatever function you're calling, they will get an error, and your program or you who is talking to the name node or talking to HDFS will have to handle that error. Is correct? So the HDFS has been designed to be strongly consistent. Either the whole file is written or nothing gets written, no matter what. All right. Now we have. Did I miss anybody's question? I'm going back to the question. So if you think your question was not answered, just copy paste it. Last point with respect to, yeah. So last point which I was saying, Nitika, that in case an error occurs while writing even a single byte here or there, although HDFS has been designed such a way that it will retry writing it, and in case something happens, something goes wrong, it's not able to write at any level, you will get an error. You will get error immediately, and it is your responsibility as a developer or responsibility as a user to handle all those errors thrown by HDFS. Okay? HDFS has been designed bottom up with very strong consistency in mind, and sacrificing at times the high availability or the high throughput. At times, it has been designed to basically handle to provide you a very consistent data. Is name node contain the details of Algedo? Yeah. So for name node, whether we are storing the data as normal file or Algedo compression, it doesn't matter much. And Algedo is like .zip file, just like that. And name node will not differentiate. It will just say that your file name is something.algedo. That's all. It will not say that. So Algedo is like .zip, just that Algedo format is designed such that even the parts of the data can be unzipped. In a zip file, if you slice a zip file, split a zip file into multiple parts, you cannot unzip each individual parts without the presence of other parts, right? If you had experience in splitting files and try to unzip it, you will realize that you must have faced this case where zipping file you cannot unzip it without presence of other parts. But in case of Algedo, the compression has been designed such that it is fairly fast even if you are uncompressing parts of it, and that's why it suits the format, because our blocks are basically parts of the whole data, right? So if the data is compressed using Algedo, we can decompress it and then utilize it. Make sense to you? So what we do is we take 1 million file, then convert an RCA file. You can say RC file right now. We'll talk about it in future again. And then we zip it with Algedo. If you have too many small files, if they have plain text files, then you compress it. Okay. And in case it's a binary file, then you generally don't compress it. Generally, most of the data is already in the well compressed format. Make sense to you now? In case you did not understand Algedo or RC file, do not bother. We will again address these issues. Okay. And any other questions for me? All right. So this was a little bit more detail of what we had talked yesterday. Yeah. So basically, Algedo or compression algorithm is yes outside the Hadoop ecosystem. It's just that the Algedo fits our requirement because our files are sliced into parts. Okay, make sense? Now, all right. So good. So Vivek's question is that when do we decide to go for it or not? Whenever you are dealing with some data where you think that compression can help, you go for Algedo. Okay. But RC file you will require to create when you have too many files, then you generally go for a composite file. We'll talk about that format again. And Algedo you will go for whenever you need compression. Okay, and compression you generally need whenever you are dealing with plain text data or a data which is not processed and compressed. Good. All right, now let's move ahead. Okay, so everybody clear about the way HDFS works? These two diagrams are clear to everybody? All right, so in this diagram, everybody is clear about the rough ideas. If you have a specific components you want to know the definition, just shout out loud. Here we have Flume and Scoop. Flume is for import export of the data from unstructured at a very fast speed. Scoop is for importing exporting data from existing database to HDFS, HBase or Hive. HDFS, Hadoop Distributed File System, is the file system which is the backbone of the whole game. We have yarn, which is a sort of a computing system. Yet yarn means yet another resource negotiator, on top of which other systems keep on running, such as MapReduce, Spark, etc. And we have HBase for the structured data. Hive is a query language, SQL interface basically. So Hive basically converts every query into MapReduce and then execute on the yarn and give you the result. Okay. Pig is similar to SQL but designed for distributed computing bottom up. Mahout is a library of algorithms for machine learning and statistics. Oozie is a workflow engine, and when you have a big project, you will have some parts, some SQL interface, some code done in SQL, some code done in Pig, and some part for Flume where you're importing data, some part in Scoop where you are again importing or exporting data, and some part would be your MapReduce. So in such scenarios, when you have to combine all of the whole process together, you have to stitch the whole process together, that first import my data, run MapReduce to clean my data, then import that data into SQL, then run Mahout on top of it, and once that Mahout is done, then send back the data via Scoop to our web server. So such a workflow is possible using Oozie. Now, Nitika's question is, HBase can't be used for querying. HBase is a data store. So actually, I should write it like this. These NoSQL databases, so-called databases, are more like a data store. They don't have a query language. They don't have all the features which are required for a standard database. All right. So HBase does not have a query like SQL. So you use Hive. So Sanjay's question is, but how does HDFS normalized? Okay. Now, Sanjay's question is, how does HDFS normalize unstructured data? How it can combine unstructured data with structured data without common data model? How does data communicate with each other? Okay, so HDFS doesn't care about whether your data is structured or unstructured. It behaves as if it knows nothing about your data. It has no concern about what format your data is in. Okay, it takes your data. HDFS client will take your data, slice it ruthlessly at 128 MB and create blocks out of it. Okay, and whenever people are asking for this data, people as in either you or you are asking for this data through your program written in MapReduce, that time your program or the underlying layer is responsible for understanding or mixing this understanding or making the meaning out of your unstructured or structured data. All right, so it is the program, it is the underlying, the input formats we will talk about in future, that takes care of making sense out of your files, sense out of these bitwise data storage, or the blocks and the binary data. Okay, make sense to you? So as we go ahead, your question will keep become more clear. All right. So HDFS doesn't care. Yeah. So it's like breaking. You want to make an omelette. You just take uh, egg and put it in there. How can I explain in that analogy? So basically, HDFS doesn't care whether you are putting eggs for the omelette or you are putting a fruits. It doesn't care. For it, it's just a bunch of stuff which is in the format of bytes. Make sense, Sanjay? So we will talk about more because when you will be writing programs or you will be using SQL, how will it interpret? All right. So HDFS is like underlying layer where you took a normal file system and made it distributed. The way in a normal file system, you had something called a file allocation table. That table has been replaced by name node, and rest of the tracks have been replaced by data nodes. So that analogy, some of you, for some of you, that analogy might click. So the whole HDFS behaves like a big disk for you. You take the file, you give it the file, and then you could take the file. That's all. Data in and data out. All right. Sweta's question is: suppose have an employee table like one we have in Oracle, how that will get stored in HDFS. So generally, when you have an employee table, you do not generally store directly into HDFS, or it's like saying that how can I store a table into a file system? Either you export it into CSV, or so the general way is you take your data. If your data is very structured, you put it into HBase. HBase will indirectly store the data into HDFS. The way we have Oracle database, but at the end of day, Oracle database is storing the data into the file system. Similarly, HBase is storing the data into HDFS. Make sense? What is the difference in process between MapReduce and Spark? That is a brilliant question, and I would delay it. I'll delay the answering of it, though I will describe right now. The way MapReduce has been designed is to process petabytes of data. Humongous data, but slow. Humongous data, but batch wise. Okay, while uh, humongous data that cannot fit into the memory, even the whole cluster, that kind of data is handled by MapReduce. But in case of Spark utilizes your RAM to a very high level to give you the immediate results. So Spark basically gives you enormous control and immediate response, while MapReduce says, hey, give me the bunch of work, I'll get it done, and I will let you know once it is done. While Spark says that, hey, I'm doing, just hold on. Okay, I'm doing, just hold on. In case there's an error, it will immediately tell you that this has failed. I cannot do much. Okay, so that's the difference between the way the psychology of both the tools. So, but in general, Spark is probably going to compete very well with MapReduce and will be utilized in lots of many cases over MapReduce. Okay, now I forgot to answer one question. How a web application connects to Hadoop ecosystem to get the data? Very good question, Sweta. So the Hadoop ecosystem, so when we say Hadoop ecosystem, it means it means all of these components. Good. Now let's imagine for time being you are an e-commerce company planning to display the recommendation on your website. How would you display those recommendations? There are two strategies into it. One is, after you have done all the machine learning computation, everything, you push the data back to MySQL. So generally when you are doing an insight, you are developing a report, the output is generally far smaller on top of a bigger data. Therefore, the output can be easily stored onto your MySQL. So recommendations can be easily stored into MySQL. Or if you do not want that to happen, you can access HBase, Hive, as well as Hive as well as HBase. You can access like a service. Both HBase as well as Hive provide you a REST interface as well as JDBC kind of interface, using which you can get the data from both. All right. So your web application will connect to Hive and get the recommendations or get whatever output of your whole process is, and then print it on your web application or display it in web application. So where is MySQL in this? You see the structured data here just below scoop. This is MySQL here. All right. Yeah, because that is correct. So Spark is mostly real time. Real time, when real time has multiple meanings. So I would not right now say real time. All right. But the psychology is same. While Spark is immediate, MapReduce says that I have got other stuff also to do. You give your work, I'm putting it in the queue. If once it's done, I'll let you know. That's the psychology MapReduce carries. So Sweta's question is, can you explain what is yarn? So just have a little bit patience. We'll go into the details now. All right. I think we are in the right moment to move ahead. Okay. Yeah. So Nitika's point is that Cassandra is a NoSQL database, but there we are able to run the query. Yes. So Cassandra qualifies to be called a database. Most of these databases, which we call NoSQL databases, they do not qualify to be called databases. Okay. Most of them are mostly data stores. Okay. All right. Yeah, you can call it that way, but people call it NoSQL database anyway. Everybody seems to be calling their data stores as databases. Okay, memcached, for example, is a key value store, and we have started calling it NoSQL database. Okay, so that's a bit jargon stuff, and yeah. All right, so now is the time that we move on to our actual stuff. So, so that was a good recap. Yes, that is correct, Sweta. All of the components are having an API, either REST-based or a Thrift API. There is something called Thrift Web Service Layer. So almost all of these components have Thrift layer via which you can call the services. All right, we will talk about those as and when we discuss each service individually. All right. All right, so let's move on to something called compute engine now. We talked about the basic layer of Hadoop distributed file system. Now let's move on to the compute engine. Okay, so here is my question to you. How fast can 1 gigahertz processor sort 1 terabyte of data? Sorting means ordering data by ordering data by certain field. All right, so you have 10 billion names having 100 character each, and you've got 1 gigahertz processor with 2 GB RAM and 1 terabyte of data. How much time do you think it is going to take to sort this data? I'm not seeking an approach, how will you do it? I'm seeking your estimation. Okay, because we all are under the impression that database sorts the data very quickly. Okay, so my question is that how much do you think it will take your computer to order 1 terabyte of data? Nitika says 2 hours. Okay, so on what disk are you storing this 1 terabyte data, Nitika? Is it on hard drive, solid state drive? What kind of disk is it? Okay. So Sayed, I'm not looking for a correct answer. There is no straightforward way to approach the computation because there are too many variables. And okay, Sweta says 10 hours. So I'm just looking for your gut. I'm just looking for your instinct, a rough estimation. How does, what does your feeling say? How much do you have, have you ever tried to sort some data? So so Pop says 6 hours, Vikas says 6 hours, Sweta says 10 hours. Okay. Do you think it makes sense? So Vikas Mishra, do you mean 6 minutes or 6 hours? Anybody else? Just give me a rough idea. I want to understand that. uh, Harshal says 4 to 5 hours. Okay. Anybody else? Just rough estimations. All right. Good. So yeah. So almost everybody is in hours. So I'm happy. And there is no straight answer to it. So it takes around 6 to 10 hours. And this much mistake is fairly possible. Some people might be having different RPMs of the disk, different different rate at which you can read from RAM, and other factors. Okay, some of you might be using solid state drives. So if you are using solid state drive, it generally takes around 6 hours. Otherwise, it might go up to 10 hours. So ordering a terabyte of data takes close to 10 hours. At least for me. Maybe my system was slow, but it took me close to 10 hours. Though few people claim that they are able to do it in 6 hours, but I'm not sure. Okay, so the idea is here, why am I talking about sorting? Because sorting is probably the mother of most of the computing problems. Okay, sorting is probably the mother of all computing problems. Let's say how it is. Sorting is, we'll talk about that again. So most of the big data systems, they compare against something called sorting benchmarks. So there is a website called sorting benchmarks. Okay, so here there is a website where everybody keeps competing every year. Okay, and many systems have been competing, and this time Apache Spark is also in a race, and it seems to do a pretty good job. Okay, so Hadoop was good up to 2009. 2013 it was a winner. 2013 it was winner in both cases. 2014 2014, in neither of the cases Hadoop is there, but Spark is winner so far. All right. So there is something called sorting benchmark, and it's very important for any engineer or everybody to understand the sorting problem. All right. Now, the what is wrong with the 6 to 10 hours? We might require faster sorting. We might require sorting on a bigger data, and we might require sorting very often. Okay, every imagine if we require sorting of 1 terabyte data every 4 hours, then this whole scheme fails because it will take a minimum of 6 hours, which means we'll never be able to do it, right? So the other, a quick benchmark of the biggest data is of 10 petabyte done by Google on 8,000 computers in 6.5 hours. Okay, so that's about sorting. All right. Now, when we talk about sorting, so let me open up another one. Do you think sorting matters in this SQL query? Select star from my table where column 1 equals some value. How does sorting matters in this query? Anyone? Vivek says yes, it matters. And just give me a hint how. Perfect. Good. Good. So indexes, if you remember, indexes in SQL are basically sorting and then unique, right? You take all the words from the book, or all the words from the column, sort them, and then create the unique list, right? So if you have indexes on column 1, then this query is going to be extremely fast. If you don't have index on column 1, then this query is going to be very, very slow. That is how the sorting matters in this query. Okay. Now next is, what about select star from my table group by column 1? Do you think sorting matters here? Anyone? So if you remember, whenever we want to group our data by a particular column values, then we generally use this syntax. Yes. So whenever you are grouping something, grouping is basically sorting and then unique. Okay. All right. What about joins? What about joins? If we are joining two tables, select star from table 1, comma table 2 on A equals B. Do you think sorting matters? So join between two tables, what you do is under the hood, you basically sort table 1 on A and table 2 on the basis of column B, and then then database tries to join it. So you can see that every operation in databases is all about sorting. An interesting insight is that sorting is the one that takes maximum amount of computation other than scanning of the data. If you're scanning the data step by step, or you are trying to read too much of data from the disk, that is far more time consuming. And after that, the other thing that is time consuming is sorting of the data. All right. So basically every problem of the SQL kind of problems can be solved with the better sorting algorithms. Okay. Now, all right. So sorting technique also means, one is how are you doing the sorting, other is in the memory or on the disk, or are you utilizing multiple computers simultaneously to do the sorting. Okay, and that's what is whole MapReduce about. Okay, we will go to MapReduce later. Here we will first talk about how to get the work done by multiple computers simultaneously. All right. Uh, so time taken. So Nitika's question is, time taken. Does time taken depends on the RAM? My answer is, it takes on algorithms, what kind of strategy you are using. Then it takes on RAM speed, RAM size, data bus, and disk read and write. All right, disk read and write speed. Make sense to you? So these are the few things that matter when we talk about time taken to um, to sort out the data. Okay, and the algorithm is the one which decide how to utilize things. Okay, how to make sure that things are done parallelly. While one process is reading data from the disk, which is slower, can other process do the sorting of the data? So there are many components when we talk about the search. So, so what kind of sorting algorithm is used for big data on Hadoop ecosystem? There's something called distributed sort. We'll talk about it soon. All right. Now let's talk about components of the computation engine. Okay. So computation engine up to Hadoop 1. First, let's talk about in terms of Hadoop 1 terminology. There is something called again job tracker, and there's something called task trackers. Okay, so job tracker is the one who you order that can you get my work done, and this job tracker asks task trackers to get the stuff done. Okay, so job tracker will give command task trackers and get the work done for you in parallel. All right, so this is a very simplified view. So you ask something, let's say get the data which belongs to somebody. You ask that to job tracker, and job tracker assigns parts of the work to each of the task trackers. All right? And so the other way to look at it is this. So client like you comes to job tracker goes to each task tracker and then hands over the work over there, and once that is done it reports back to the client saying I am done. All right, now you might ask that how does it help minimize the data transfer? So whenever we ask job tracker to get something done, we also tell the job tracker that, hey, I want to process this file. I want to process this file. Can you help me processing this file? So job tracker will ask admin node that where is this file located? Which all machines contain this file? And it will find out all the task trackers running on those machines, and it will assign the work only to those machines. That can you just process our data, right? Because the data is distributed across the cluster. So it is always better to do the computation on the same machine containing the data as opposed to some other machine where the data transfer is required over the network. All right. So you have got job tracker. You tell job tracker, please process this file using this logic. Okay. Job tracker takes that assignment, goes, figures out where is this file which you want to process, and find out all the data nodes containing that file. And once it has found out all the data node containing the blocks of that file, it will find out where are the task trackers located nearest to the data and get your work done parallelly on all those task trackers. Okay, this way the data transfer is heavily minimized. This way the data transfer is heavily minimized, and that's what makes the processing really powerful and fast. All right, so we did two things. It did two things for us. First, whatever logic we had, it executed parallelly using multiple computers. The second thing it did was, since our data was already distributed across the network. Okay, so job tracker, we asked job tracker, so I'll go through this one. So it did two things for us. First, it utilized multitude of computer to get your work done. Second, it executed your logic closer to the data so that you did not have to transfer the data from one computer to another. All right, let me go through the details again. So the way it happens is, you as a user copy your input data files onto Hadoop distributed file system. We also call it DFS instead of HDFS. We can also call it DFS. So the user, let me just I've forgotten my password. All right, forget it. I'm going to discard this and take a full screen snapshot. Now here we go. All right, so the way it happens is, yeah, now, so you as a user copy your data to HDFS. Okay, here, before you start to work on this, you will basically copy your data to DFS. Then you will submit your job via client to the job tracker. Okay, so here you will find out where all, basically job tracker will find out for you where all the parts located on the file system. Okay, now once it has found out where are the input splits located, then it will create a job queue. Okay, I think I'll first describe here because you guys are asking again. Yeah, so Sweta's point is, can you explain with sorting example along with it? Don't worry, I'll make sure that you all understand it. All right, so job tracker and admin node, there are these two things. Job tracker knows about the admin node of your HDFS. We talked about the bottom side, the below side, the lower region below this line earlier, where we have admin node and data nodes. Similarly, generally on each data node, we have task tracker process running. Task tracker is just a process just like data node running on the same machine, data nodes generally. Why? Because we want to execute our logic near to the file system. All right. Now, whenever we ask job tracker to do something, we generally talk in terms of, here is my file, can you process this file? We tell job tracker, here is this is my HDFS file name, which I want to process in terms of I want to find out the unique name in it, or I want to do something about it. We tell that as a MapReduce logic or some other logic. We'll talk about that again. So we tell job tracker, here is my logic, here is this file name which we want to process through this logic. Can you get it done? Job tracker goes to the admin node, says that, can you tell where are the blocks located of this file? Admin node tells that these are the data node containing the blocks, and now it's up to you what you want to do. Now job tracker finds out which are the task tracker processes running on the data nodes containing the blocks, where is this file located, and thus only on those task trackers which are very close by to the data, it executes it executes the logic you had handed over to it. All right. And once it is done, it responds to you. It gives you the response collected from all task trackers. So this is how the general computation happens over this job tracker task tracker. Okay. So in this process, the same part has been depicted to you. You as a client copied the data to DFS and then you submitted it. Job tracker, after figuring out where are the blocks of data stored, next step for you is that you here there is one more interesting aspect about it. So job tracker initializes something called a job queue. Job queue is like, if you have seen any of the workshop floor where there are a lot of workers and there is one supervisor, the supervisor keeps track of jobs. The job one has been assigned to this particular Shaw, this particular workman, and job two has been assigned to this particular workman, and so on. For each piece of the data, it creates this individual work for these individual tasks. And in case any of the task tracker goes down, it assigns the same work to somebody else who is closer to your data. Okay, so the file which we want to process was on data node 1 and data node 2. Now the task tracker running on data node 1 and data node 2 is the one which we will select for processing of our work. I mean, job tracker will do that for us. In case any of these machines go down, the same work will be assigned to somebody else which is closer to our block. And remember that each block has got a replication copy. So in case there is no node task, there is no task tracker closer to the block one, the first copy of the block one, the work will be assigned to somebody else which is closer to the second copy of block one, and so on. All right. So basically the idea is to process the file. No, we don't have a secondary job tracker. Okay. And that is probably the reason why we call MapReduce as sort of a batch processes. Okay. Job tracker is not highly available. In case it goes down, admin goes and checks why our job tracker did not run, it kicks it. All right. So we will talk about maps in detail. Right now, I'm just generally talking about the kind of execution it happens. Maps is the individual unit of the work, and probably this is the better diagram. All right. Now, we talked about job tracker and task tracker and the data locality, meaning the work is given to the task tracker which is closer located to the block of the data. All right, let's take a 5 minutes break. Okay. All right, I'm back. So, are you guys back? Should we start? So yeah. So Sanjay, I agree that we are going at a little slower pace, but the thing is that initial sessions are generally slower, and then they pick up the pace at a later point of time. And I would like to spend more time in clearing your doubts now as compared to the later. Okay, don't worry. I mean, in case we do not finish, uh, I mean, we'll. I mean, it's completely okay. It's a usual pace. All right, nothing to worry on that. All right, so great. So we talked about the work getting divided, and the work is allocated to the nodes that are closer to the data, right? But what exactly is going on in terms of what is map, what is reduced? Now let's have a look at it. So whenever you are giving the work to Hadoop MapReduce, you generally give few things to it. First, you tell that this is the file which I want to process, okay? And second is you tell that this is my logic called map, and this is my logic called reduce. So you hand over the logic to MapReduce in the form of functions called map and reduce. This is the logic you write. This logic can be in Java, that logic can be in other programming language. So you write this map and reduce logic and you hand it over to Hadoop. Now what happens with that map and reduce logic? So on each block we create something called a split. So this you can think of each block: split 0, split 1, split 2. It's corresponding to each block we have split. Okay, on each of the data node this is what is going on data node 1. We pick up a block, we take the data record by record, pass through your execution logic, whatever you have written, and whatever is the result of map reduce, whatever is the result of map, we start sorting it. Now you may ask, sorting on what basis? So map is supposed to give the output in the form of key and the value. Key is the one which is the foundation of sorting the data. On the basis of that key, the data is sorted, and then once the sorting has finished on all of this, the data gets merged on one of the nodes here, and then once everything has been gathered on this node, the reduce function is executed for each key on top of all the values. Okay, so what does map take? Map takes a record at a time, which is a part of our data, okay? And whatever is the output of map, it is sorted and then it is merged at a single place. After merging, for each key, all the values are basically reduced. All right. So now you can think of it as like a group by clause. In group by, we select that our data has to be grouped by a particular column. That is the key here. Okay. And then this sorting happens, and then a reduce function is like aggregation function. For each key, all the values are aggregated together in reduce. All right. So whatever function you write in map, you have to bear in mind that your map function will execute on top of each record provided by the file system, and then it has to generate key and the value. All right. And whenever you're writing the reduce, So what is the input in split 0? So whenever we are processing a file, we tell we tell Hadoop that we are trying to process a file, and these are the blocks: block 0, block 1, block 2 of that particular file. All right, this is how you can think about it. If you remember, whenever we store a file in HDFS, it's broken into parts, and these are those parts. And on top of each part, our map function is being run. It will generate key and value, and then all of that data is sorted and copied and then merged together again. And once merging finishes, the data is again sorted, and here you have this data which is sorted by keys as provided by your map function. And so key and the values, there will be multiple values. Remember, there will be multiple values for a key, and all these values are combined together using a function defined by you called reduce. Now, you may provide a reduce function or you may not provide a reduce function. It is absolutely up to you. All right. And sometimes your input data is already in key value format, then you don't define the map function. So you can, yeah. So Nitika. So this input, this each block is each split. So right now you can assume that we'll go into that detail a little bit later. Okay. So you can right now you can think of each split equivalent to each block. Okay. You can think of the block was raw data, and this split is sort of an envelope on top of that raw data. All right. So is everybody with me? Did I confuse you? Yes, reduce is also your logic, your function. Okay. The duty of your reduce function is to take multiple values for a key and combine them together. Just like when we say select star, select A comma sum of B group by A. All right. That is, the sum is our reduce function. So Vikas's question is, the map program runs at data node and reduce runs at name node. Okay, so that is correct. First part is correct. Map program runs at data node and reduce also runs at data nodes. Name node doesn't do anything. All right. Okay. So maybe another name node, and that. Okay. So name node is nowhere in the picture right now. All right. Name node is nowhere in the picture. So this is one data node. This one. Okay. Let me draw some things. So this one is one data node. This is another, and this is another data node. These are three data nodes, and there is the fourth data node which is being utilized for combining work together. All right. These are all data nodes. Okay. Let me take a step back. Let me take a step back. No worries. Yes, there can be multiple reduces running at one point of time. Yeah, that is correct. All right. Again, so you wrote function called map. So there is another machine on which, since this data is on the blocks, right? End user has asked you. So end user, which is you, has asked Hadoop to run its map and reduces on top of a file. So map is run on parts of the data located at multiple machines. All right. And once the results are given out by map, the data is ordered by the key given by the map each function. So your map function will give out key and value for all the data. Okay, and that data is sorted, and after sorting the data is copied to another node, and once the copying is finished, the data is merged, and after merging the data is passed through reduce. All right, sorting done according to the key, that is correct. That's the whole role of the key in MapReduce. Okay, so map's duty is to specify the key. Make sense to you? And once everything finishes here, the work goes to HDFS. Okay, the output goes to HDFS. Reduce can do things like summation of all the values for a key, multiplication of all the values of the key, computing average, median, or square root of all the values for a key, and so on. Okay, there are anything you can write inside map this reduce as well as map. Okay, reduce can do anything, a complex thing as something like square root of all the squares, summation of all the squares, and so on for the all the values for a key. So reduce is executed for key and all its values one at a time. So reduce gets key and multiple values as the argument, and reduce does the work, and whatever output reduce gives, it goes to the HDFS again. So Nitika's question is, if my data is already in key value pair, so split contains your data in key value pair, map does not have to do anything in those cases. All right. Map function will not do anything at all. Okay. There you can skip the map function. I'll show you that part also. Replication in the name node happens only after MapReduce. I did not get this point. So here we are talking about um, the computation part. Replication is with respect to the storage of the files. Or you mean to say here, this one? Yeah. So whenever we are creating a file into HDFS, the whole process of creation of file starts, meaning it will create, go to name node and create a file, and then go to data node, start writing the data to the data node, and then data node starts replication, and so on. So yeah, Tarak, it's okay to you ask that question in public, because I have to anyway answer it. So reduce basically computes on the data it has received from computed data from map. Yes, that is correct. The only difference is, in case same key is on multiple data nodes, that is merged together, and those values are combined together using a reduce function. All right. So we will have enough time to go through this again and again. Don't worry. In case you are still having confusion, feel free to ask questions. Okay. This is something which takes a bit of time and a bit of time to sink in. All right. Now, if you look at it closely, what is it that we did here? What is it that we did? First, we ordered the data by the key, then we combined it, and then what we did, for each key, there might be multiple values, and those values can be combined in whatever choice, whatever way you want. So you can use reduce a function to combine those multiple values for a key. Okay, you can do average, you can do median, you can do square root, whatever you want. All right. So now question is that then where is the processing happening? So processing is happening in the form of map converting the input into key value, and sorting is the one which has been delegated to multiple nodes. Okay, so the sorting of the data which takes maximum amount of time has been delegated to each these nodes. And note that merging a sorted data is far more easier than trying to merge and then sort. Okay, so we sort the data here, and then merge and then sort it again. Yes, we will have a typical big data example, no worries, Vivek. Okay, right, sorting is done generally by a distributed sort. Okay, here those are the usual sorting algorithm. What is important to note that sorting is happening in two steps. First it got sorted here, then merged, and then again sorted. All right, so please note that it's actually easier to sort a sorted data. Imagine first data node has keys in this order, sorted. Second data node has these, and third data node has this, or you can also put like this. Okay, you can see this. So imagine that the data from these three nodes came like this. Okay, the data from these three nodes is first gave these are key. We are not talking about value, only the keys, because data is sorted by the keys. Okay, now once it has been sorted, this is sorted, right? You see this is sorted from left to right. Once these are sorted, merging which is happening here is actually a straightforward process. Okay, and how does it happen? You choose the head of each one and pick up the smallest one from there. And which one is the smallest one? This one. We remove that, again we compare. All right, and whatever is the smallest, we pick that up and put it here. Okay, make sense? Out of this, what is smallest? Anyone? Quickly. So it is 3 and 3. Both are removed from here. So I'm trying to show you stepwise how a merging happens and how simple it is to merge data. Now 4. All right. And now we pick up 5 and everything afterwards. Okay, so we have successfully merged the data in a single pass. All right, so the merging of this already sorted data is actually a fairly straightforward process. Yes, that is correct. So now grouping these together is easier. Okay, so you can visualize them in case you can visualize them like this. Okay, you can group it whatever you want to do, it does it automatically for you. That's correct, Sayed. So why we do not sort in reduce part, we do not sort. Okay, what we do is how to merge these three keys together. That's what is decided inside reduce. If you do not want to merge these three the same keys, the three values for the same keys, if you do not want to merge, don't merge. It's up to you. All right, perfect. Everyone with me? Great, great. So this is the general map reduce process. Now we go one step forward. Now as you can see that since there is only a single machine allocated for your map reduce, for reduce here, okay, so sometimes this machine might get very heavily overloaded. Therefore, there could be multiple reduces like this. Okay, so here we inform Hadoop that we want two reduces. We want two reduces, and what Hadoop does for us is it takes the output of map and puts that output into two buckets. First key goes in first bucket, second key goes in second bucket, third key goes in first one, fourth key goes in there. On a certain logic, it divides the keys into two buckets. Okay, and then takes the first bucket to the first reduce, second bucket to the second reduce. Similarly, on other data nodes, it takes the first bucket to the first reduce, second bucket to the second, and so on. And rest of the process of merging and execution of reduce is identical. Okay, that is how multiple reduces function. What is the need of it? Okay, so the need is since your data might be very huge, and this node, this boundary you see, this node running this merging and reducing might get humongously overloaded, while on one side our work is getting done by say 1,000 computers parallelly. This is three for this example, but the there, if your data is spread across thousands of computers, if you have a terabyte of data, you might have 8,000 parts of it and 8,000 data nodes parallelly running your work. Now, so after merging the data of 8,000, the single node of reduce might get overloaded, humongously overloaded. Therefore, you might require multiple reduces. Okay, and when you say that, hey, we can tell Hadoop that, hey, this is my file which I want to process, this is my map function, and this is my reduce function, and this is my output folder in HDFS, and these many reduces I want. As a number, I tell that I want 3 reduces. So there will be 3 buckets here on each of this, and so on. So yeah, Sweta's question is that then it will be possible that a key is on both the reduces. Brilliant question. So there is no possibility of this happening. That is how it is decided here. When Hadoop is deciding that a key should go into first bucket or second bucket, the same logic is applied on all machines. Okay, so if the same key appears on this machine, it will go in first bucket if it has gone into the first bucket here. If there are 10 buckets, then also, okay, if you have 10 number of reduces, then you will have 10 buckets, and the same key will always go into the same bucket, and the bucket will be carried on to a reduce. Okay, so does it make sense to you? So this logic of taking a key and putting it in bucket is called partitioning, and this can also be customized by you. You can define whether a key can go into first bucket or second bucket or third bucket and so on. Meaning, should a key go to first reduce or second reduce? That is up to you to define. All right. Now, so Nitika, you got your answer, right? All right. Vivek's question is, so even if reduce is distributed, the first reduce will only begin once all the merges are done and sorted. Brilliant question. Yes, answer is yes. But at Hadoop internally, these processes are, they are always trying to parallelize it by hook or the crook. Okay, so it is yes, it is fairly true. Okay, all right. Yeah, all right. Let me take a copy of it. So now let me just read out the questions. Okay, so even if the reduce is distributed, the first reduce will only begin only after. That is correct. And yeah, to make two or more reduce possible, is there any setting in the console? Yeah. So whenever you, I'm trying to answer this question. So whenever you are assigning the work to MapReduce or Hadoop, that can you execute my maps and reduces, you specify that how many reduces do you want to run. Okay, there is generally no limit, but for optimization reasons there are a strategy we will discuss on how many reduces you generally should keep. Okay, okay, so Nitika's question is, for example, I'm talking about 10 buckets for each, but in one of the block there is less than 10. No, there cannot be less than 10. All right. So if you have, when you ask Hadoop to do something, you tell that, hey, I want to run only one reduce or 10 reduces. Okay. If you have 10 reduces, you will have 10 buckets on each machines. There are chances that one of the buckets is empty, right? There are chances that one of the buckets or few of the buckets are totally empty. In those cases, nothing will get transferred over the wire. Here, the merging there will no transfer here. Okay, but the buckets will be there in order to put the data in those. All right, makes sense to you? Okay, okay, Vivek's question, let me reiterate what is Vivek's question. So his question was, if you look at it here, merge can only happen, this merge will start only when all the data has arrived from all these three machines, right? One data is coming from this first bucket is coming here, first bucket is coming here, first bucket is coming from here. So all three data nodes are sending their one bucket to this machine, right? So and if you see that this merge cannot start happening till a point that all the data has arrived from all the nodes, right? So, and one more thing you should note here is, in today's time, Hadoop has actually made it really, really fast. The transfer starts happening as and when map is spitting out the data. The transfer keeps happening over here. And merge also starts happening, because it's okay to merge the data and we will remerge later when the new data arrives. Okay, so because you can merge part of the data, as we said earlier, like if you have I missed out that part. So let's say let's say we have this, okay, and we are trying to merge, so we can actually merge these two, and then whatever is the result we can merge them together and so on, right? So all of this can happen to a very large extent in a parallel manner. Okay, those are little bit of internals. All right. Again, same diagram where I'm showing that you as a user ask task tracker that, hey, I want to process this file using this map and this reduce, these many reduces I want, and get it done howsoever. Job tracker sends the work to task trackers closer to your file, and task trackers do the maps and reduces and give back the result to you. All right. Now, there was something called Hadoop 1.0. All right. There was something called Hadoop 1.0 where there was a single thing called map reduce. Okay. The task tracker, job tracker, as well as this map reduce process was which last point, Nitika? I was basically in the last point, I was generally talking about the same diagram where user is you as a user is asking job tracker to get the work done. And the way you ask is you tell job tracker that I want to process this file. Here is my map function. Here is my reduce function. Can you get it done, please? Okay. And I want these many reducers. All right. Okay. So So in Hadoop 1.0, the both things like execution of the work on each machine as well as the map reduce paradigm both were part of the single piece of code, meaning this was monolithic. Okay, but in Hadoop 2.0 they did a smart move and with which was very successful, and because of which there are a lot of more innovation possible as of today. So they broke down MapReduce into two parts. One part is essentially the execution of the task, whatever is the task, and other is MapReduce, where each unit of work is measured in terms of maps and reduces. And so it was broken down into two so that other people can also utilize this ability of Hadoop to execute work in parallel manner on multiple computers. Okay, that is why Yarn was the MapReduce was broken into two parts: MapReduce 2.0 and Yarn, and because of which today we have these many competitors to MapReduce. Right now, you can see that there is something called Spark, which is basically equivalent to MapReduce running on top of Yarn. Yarn's duty is to allocate resources on various machines, get your work executed no matter what is the work, while MapReduce forces you to write only maps and reduces. It can only do things like maps and reduces and nothing else. All right. And because of this breaking of MapReduce into two parts, it opened the door for more kind of computings. Okay, not only in terms of MapReduce, but in a whether you are trying to process a graph, you are trying to do a lot of in-memory computation using Spark, or you are using HBase, yeah, and so on. So Yarn is yet another resource negotiator. Yarn's duty is whatever work you assign to it, the job tracker, task tracker thing is the duty of Yarn. All right. All right. So basically, you ask Yarn to all these programs, whether MapReduce or Interactive, they all talk to Yarn and they internally get their work executed using Yarn. Yarn makes it possible that to utilize your cluster, a multitude of computers. All right. So Yarn basically supports for the workload other than MapReduce, scalability, compatibility with other thing which happened was when this translation from Hadoop 1.0 to Hadoop 2.0 happened, nothing nothing with respect to developer changed. Whatever programs they had written for older MapReduce ran exactly the same way on the newer Yarn. Okay, and now it was possible to do the resource utilization better, separate, independent of MapReduce. Okay. All right. Now, job track. Other thing happened was there was a simple thing called job tracker, task tracker. So, job tracker became something called a resource manager, global resource manager. This is job tracker basically, and task tracker became a node manager. Okay, and these are the essentially eh, eh, few more components introduced as part of Yarn. All right. So you can think of resource manager as job tracker and node manager as task tracker. Resource manager is single while node manager runs on each machines. All right. So this is what happened when the translation from Hadoop 1.0 to Hadoop 2.0 happened. All right. And this is a complex way of representing the same thing. You have node manager, node manager, node manager, and you have resource manager. For each application, say MapReduce, you will have these buckets to manage each applications. Okay, so we are not going into too much of detail of Yarn. If everybody wants, I can take it up in the next session. All right. All right, let's have an overview of how does things look like, a little quick hands-on. Okay, so first of all, let's have a look at the web interface. So all of you have the login password for the Cloud Labs, right? Under the installation document, you can see the login password. There you will see the Ambari. Ambari is essentially an interface using which you manage your whole cluster. Okay, it shows you the whole statistics, the all of the statistics about your cluster. We have disk usage which shows and these. Other than this, what is important is you have name node, secondary name node, and data nodes. All right, also please notice that using Ambari, you can install newer host very easily. You bought a new computer, all you need to do is you go here and say add new host. Give their IP after and provide the SSH private key, and that's all. All right. So it does a lot of things for you. Basically, it helps you provisioning anything. At the same time, it also shows you what is running on each node. So I clicked on, we have 4 servers. If you go into hosts, you will see that there are 4 servers right now. The Hadoop one is running HBase, Hive server, MySQL, name node, resource manager. Resource manager is job tracker, okay? Resource manager. And there is something called webcat. We don't need it now. We also are running a data node here. That is something you will find strange. We have name node as well as data node. on the same machine. Generally, it's a little bad practice, but we are becoming we are being a little greedy. We want to utilize the hard disk space of Hadoop 1 also. Okay. Now Hadoop 2 will have these all services. You can see here secondary name node is down. We can turn it on easily like this. Okay. And we have these region server here. Node manager is task tracker. Okay. Node manager is task tracker, which is part of yarn. Okay. Other than that, we have these clients. So you may not see the start these controls because you might be having you don't have the admin privileges on Ambari. Okay. So we are using Hot and Works package, not the Cloud Era one, because I prefer personally the Ambari way of provisioning the systems. The next is that in case you want to operate or execute something over the cluster, you do this. Go to Hue. Hue is running at 8000 port. This is running at 8080 port. Login password is same. So you can see this here. This is the HDFS. Okay. Before operating upon it, please create your own separate folder. Do not fiddle with other folders. Why I have kept everybody in the same folder, same login, because that way anything I'm doing, a sample data is very easier to share. Okay. So this is HDFS. So you can operate upon HDFS from the browser, and I'll also show how to operate upon this HDFS from the command line. All right. So you can create a folder, or you can upload a file. You can upload a file from here. Okay. So it will directly go into HDFS. These are the files existing already on the HDFS. In case you want to see the file, you can simply click on a file and here will be the data. Sounds good to you? Next is in case you want to operate upon other services such as Pig. But again, I like to remind you that create your own separate folder before your data get mixed up with other users. All right. So here you can operate upon various services and also see what are the jobs running on the cluster. Right now, there is not much of a jobs running here. All right. Okay. The other is, in case you are on Windows, please use PuTTY to directly log on to any of our servers. Or if you are on Linux or Unix machines, you can simply do SSH. Okay, and then provide the password. Also, on Windows, on our Linux machine, you can use SCP. On Windows machine, you will have to install WinSCP. Okay. So Vikas' question is that does Amazon also provide Hadoop like S3? They have their whole own installation of Amazon Elastic Cloud. Okay, they call it Amazon MR. You can utilize that. So yeah, are you going to explain this dashboard a little detail later on? No, I think I should explain right now. So here we have HDFS. If you want to operate, see the statistics of a Hadoop distributed file system. And yeah, that's correct. It's Elastic MapReduce. Thank you, Goel. And This is yarn. It shows what all services are up. In case you want to add a service or in case you want to add a host, you can use this. Okay. As and when we are going ahead, when we are attempting each individual components, we will go through this again and again. Yes, you can right away start using it. All right. And yeah, so let me open the terminal. In case you are on Windows, you will have to use putty. You can download putty and run it. And so you say ssh student at hadoop fun dot no big data, no big data. So as soon as we log in, we will be in Hadoop 1.no big data. And when we say ls, it will be the local file system. It is not HDFS. This is when we say ls, it's a local file system of this Hadoop 1 machine. Okay, it's not HDFS. So how do you access? So let me just go to my folder, and whenever you're working anywhere, create your own folder without getting mixed up with anybody else's data. Okay, so let's have a look at a file called here rating.csv and say we want to see what is there in HDFS. Okay, so we can from command line we can say Hadoop fs minus ls and it will show us all the files that are there in Hadoop. Okay, you can see, or should I increase the font? All right, so you use Hadoop command to access the Hadoop cluster. If you say Hadoop fs, you access the file system. So Sayed, it is in the installation document. You go to no big data, my courses. So which locate are we talking, Vikas? You mean to say locate this one, right? We have not we have avoided installing locate on these machines because it does locate is quite an intensive command. It keeps on creating the database continuously. That is why we have avoided it. But what is the objective you're trying to do? Yeah, we can do the same thing using find command. So if you help me out, so here if you go into your course under installation instruction and under this particular document, you will find the login password. Okay, I'm not opening it because I do not want to show it in this recording. Okay, all right, so Hadoop command is the one which helps us interact with the file system. So let's say we want to upload something. Let's create a file. Let me create a file. I'll use nano and I'll say my file 18 April. Okay, and so this is a simple file and let's see if it gets uploaded. Okay, so we say Hadoop fs copy from local. I created a simple file locally as in on Hadoop 1, copy from local. Okay, and then I specify my file and then put it in a folder called sgiri. Now let's check, does it exist? Does it exist in my folder? Let me go to my folder, and my folder may be on another. Yeah, sgiri is here. Yeah, we can use cat instead of nano. Definitely we can say, okay, so student and sgiri. Okay, yeah, you can have a look at it. Right now there are too many folders in my folder, too many files in my folder. So yeah, here there is no file called my file, MNOPQR here. Yeah, there is no file here, so let me just upload it. So it's copying my local file which I just created for you there. Okay, now let me just refresh it. So it has been uploaded into HDFS. Okay, so where is my file? 18 April. So you can see this is a simple file, that's what I've written. Now if you want to download this file, you can say copy to local, and provide the file name. All right, also here the other thing I would like to do here is where is my first slide? So if you want to find out where all the files related to our data exist, we can say things like this. All right, so or let me just give my file, what was the name of the file which we just created? It is my file 18 April. Right, so you can see that when I say hdfs fsck, so there is another command called hdfs. Hdfs provides you the direct interaction or the admin utilities on top of hdfs. Okay. N- so yeah, you can do on the same node as well, Vikas, no worries, right? And when you are copying things like HDFS, Hadoop, no matter from which machine you do, whether Hadoop 1, Hadoop 2, Hadoop 3, it is going to give you the same result because it's interacting to the same name node and it's interacting to the same data nodes. All right. So now it will show you which all machines does our this particular file exist. Let's have a look at what's going on here. Okay, so it says here from here to here, so it says connecting to name node, as you can see, connecting to name node which is running on this port. Okay, and this fsck file check was started by the student from this machine for this particular file at this time, and this file contains 24 bytes and there is only one block. And what does the metadata look like? It shows you this is the name of the block from here. Length is 24, replication factor is 3, and these are the data node where it exists. So on this data node 107, 170, 92, 232, these are the IP addresses of Hadoop 1, Hadoop 2, Hadoop 3, and to 201. See these are the IP addresses on which these copies of the data are existing. All right, and here it shows that what is the status of our uh, file. Okay, if you want to increase, the replication factor of this file, So we can say Hadoop fs set replication factor equals 4. Now you can see that replication factor has been set for this file as 4, and now it should have 4 copies. Alright. Now you can see that these are four data nodes containing our data. Sounds good to you? 1, 2, 3, and 4. Okay. Now you can see the replication factor is 4. Sounds good? So I'm just making a copy of whatever I have done here, so that you can also try to execute the same things. All right. So always here what we have done is, I think time is up for today. Okay. Some of you might have to rush somewhere else, so it's better that we stop here. Now here, have a look at this. So what we did was we first copied this file from local to HDFS inside my sgiri folder. After that, we checked the status of every block, and after that we increased the replication to 4, and after that we did this. Okay. Now let's see what happens in case we want to increase the replication factor to 5. Okay. Now it will show you that it will give an error that it is not able to do so. So the replication factor will remain as 4. It will. So here you can see that under replicated, okay, target replica is 5, but we have found only 4 replicas. Okay. And it says that it's only having 4 this. Okay. Default replication factor is still 3, the one which is set by there, but we have changed it. And right now we have only 1 rack. Yeah, you should not be executing such commands. Okay. It has let you execute, but it has not set the replication factor. It has not taken into consideration. They have told you that this is something which is not being done. Okay. The moment you add more nodes, it will create replicas for you. Okay. No, you can set any number of times. Now let's say we want to go back to 2. You can set it as 2. All right. Now it will become 2. So what is the use of it? Can somebody answer it? All right, let me answer it. So of course there is a big use of changing the replication factor. What is the use of? You can change the replication factor as many times as possible. If you have more nodes, if you need more blocks, if you need more copies, then set more replication. If you don't want more replication, then set it less replication. So it gives you the complete one. And with respect to your question is, what's the point of letting you set replication factor as 5 when there is only place for 3, right? because it's not possible right away to predict there is a place or not. Okay, all right. It's not possible for it to predict immediately that the target replication factor is possible or not. So it takes it, it notes it down that target replication factor is this much. If it is not able to achieve, it will tell you upfront that we are not able to achieve it. All right. All right, I think we will take everything else on the next session. Nothing to worry. Please finish all the quizzes which are available on the here. So, okay, on the instructlet here. So please finish this quiz, and session two's assignment we will talk in the next session. Now you can take the quiz as many times as possible. Okay, we'll have all the records, how many times you have taken and which one is your best score. All right. All right. So let's meet on next Saturday and take it further from here. Okay. Thank you, Tarak. So let me just take a note of it. All right. Yeah. Thank you. Bye bye. Have a good day, and thank you for the great session.